Hi everyone! Salamat sa inyong patuloy na ginagawang pagsubaybay dito sa ating discussions about mechanics of deformable bodies. Bago tayo magpatuloy guys, ay sana ay may siguro ninyo na nakapag-subscribe na kayo sa ating channel nang upang sa gayon ay patuloy ninyong nasusubaybayan itong ating ginagawang discussions. Guys, ang topic natin sa ngayon ay about thermal stresses, At magsisimula tayo with the simple background there of what is thermal stress. And so, sabi nga dito, it is a known fact that changes in temperature causes bodies to expand or contract. Depending on how the temperature will change, the body will either expand or contract. And it is also known that the linear expansion of the body as observed from experiment is directly proportional to the original length, the change in temperature, and is given by the following relation that delta L is equal to alpha L delta T, na kung saan itong ating delta L is called as the change in length due to the change in temperature, whereas our alpha is the coefficient of linear expansion, L is the original length, and delta T is the change in temperature. If temperature deformation is permitted to occur freely, there will be no load or stress that will be induced in the structure. But in cases where temperature deformations are not permitted to occur freely, because they are not feasible or not allowed, the result is that there is an internal force that will be created that will resist the supposed to be deformation. The stresses caused by the internal force are called as the thermal stress. So, ibig sabihin, kaya pala nagkakaroon tayo na tinatawag na thermal stress ay dahil sa pagpigil doon sa tinatawag nating inaasahang deformation due to the change in temperature. If the deformation is not permitted, dahil nga hindi pwede o kaya hindi feasible, so there is a load that will be produced that will resist the supposed to be change in the deformation. Kaya yung stress na paki-create ng na-produce na load because of controlling or preventing the supposed to be deformation is called as the thermal stress. Basically, there are general procedures in computing the loads and stresses that are caused by the temperature, especially when the deformation is prevented. And this is summarized into 3 basic steps that if we shall be able to apply the basic steps, these 3 steps, then solution will be very, very simple. And here are the basic steps. Number 1 is to imagine that the loads or the structure is relieved of all loads and constraints so that the deformation can be allowed or the deformation can occur freely, and if possible, we represent this deformation on a sketch and exaggerate the effects. Sabi nga, una ay ma-imagine natin na tanggalin muna natin yung loads, tanggalin natin yung mga constraints upang mapayagan natin na magkaroon ng deformation, so that the deformation will occur freely. And in doing so, kinakailangan i-represent natin yung deformations on a sketch, and if possible, exaggerates their effect para mas madali natin siyang makikita, Pangalawa, imagine natin that a sufficient load is applied to the structure to restore it to the specified condition of restraints. That is, yung inaasahan nating position o kaya naman ay condition after the temperature change. So, kinakailangan may balik natin siya dun sa kanyang specified condition of restraint. So, we shall be applying a load. Then afterwards, we try to establish the geometric relationship between temperature and load deformations, and together with the equations of static equilibrium, we'll solve the unknown quantities. Sabi nga, ma-establish natin ngayon yung geometric relation between the temperature and load deformation at kasabay ng conditions of equilibrium, masosolve na natin yung problem. At para maipakita itong basic procedure, ay naganda ako ng 3 problems para dito para ma-guide tayo kung paano mag-solve easily and systematically the problems that will deal with thermal stresses. And here is our sample problem. This problem actually was taken from the book of Ferdinand Singer, Strength of Materials. And the problem goes like this. A bronze bar 3 meters long with cross-sectional area of 320 square millimeter is placed between 2 rigid walls as shown in the figure. At a temperature of negative 20 degrees Celsius, there is a gap of 2.5 millimeter between the wall and the end of the bar. So we are required here to find the temperature at which the compressive stress in the bar will be 35 megapascal. We will be using the coefficient of linear expansion to be 18 times 10 to the negative 6 meter per meter degree Celsius and a modulus of elasticity equal to 80 gigapascal. So here in the problem, we have a bar having a length of 3 meters, diba? And there is a gap between the bar at the initial temperature of negative 20 degrees Celsius. So if we're going to follow the first step, that is to imagine that the structure be relieved of all loads and constraints so that we will be allowing the deformation to occur freely on the material, then here is what will happen. So if we shall be removing this wall, then we consider that there will be now a change in temperature. Particularly, we expect that the temperature will increase. What will happen to the materials? That it will elongate. And let us imagine that the elongation is shown, with exaggeration. This is what what will happen on the material. So you will notice that there was an elongation caused by this change in temperature. So if you are to represent the deformation with on the illustration, then this length shall indicate the change in the length of the material due to the change in temperature. And you'll notice that it has expanded or stretched beyond the supposed to be the wall, the original restraint. Considering the step number 2, which says that now imagine that there is a sufficient load applied to the structure to restore it to the specified condition of restraint. So when you say restraint, that is expected position or condition after the temperature change. So ang totoo niyan is that there must be the wall. So this is the original constraint, the original position and the expected position after the change in temperature as shown by the shadow. But because the bar is already stretched or elongated, we cannot return it back. We cannot return back the wall. What should we do is that we need to apply force, and the force must induce a deformation in order for us to restore the wall to its original place. So if we're going to do it, so let us try to consider showing the supposed to be deformation that the force will cause on the bar to bring it back to this position of restraint or expected position after the change in deformation, so that we can bring back the wall. So after that, what shall we do? According to the discussion, we need to show this deformation. What is this deformation? This deformation is called the deformation on the bar due to the internal load that is developed after the temperature change, and that is called as deformation due to the P on the bar. Then the third step is that we establish the geometric relationship between the temperature and load deformation, and together with the equation of static equilibrium, will solve for the unknown quantities. So sabi dito, kinakailangan ma-establish natin yung relationship between those deformation caused by the change in temperature and the deformation that is caused by the internal force that is developed due to the change in temperature. And therefore, we are trying to establish how is this related to this one, diba? And if you're going to look at carefully, imagine carefully, that the total deformation in the length of the material is the sum of the two elements, the gap between the initial position of the bar and the wall and the deformation caused by the internal force due to the change in temperature. So that, if we're going to establish the relationship, so we have delta L due to the change in temperature shall be equal to 2.5 plus deformation of the material due to the internal load P. And here is the relationship. Ito yung tinatawag nating geometric relationship that exists between the change in the length due to the change in temperature and the deformation caused by the internal load caused by the change in temperature. So if we're going to substitute the formula, in this formula we have alpha L equals delta L equals 2.5 plus deformation of P, where our delta L is just given as alpha L delta T, while our deformation is known to be equal to the product of PL over AE. But we know that P over A is the stress, and this is the stress that is supposed to be induced by the change in temperature, which is 35 megapascal. So if we will be simplifying this equation further, then our equation becomes alpha L delta T shall be equal to 2.5 plus stress multiplied by L over E. And if all our values shall be substituted in this resulting equation, therefore our equations become equal to 18 times 10 to the negative 6 meter per meter degree Celsius, representing our coefficient of linear expansion, the length which will be equal to 3000 millimeter, and delta T, which is the unknown quantity. Whereas on the right we have 2.5, which is a constant given, plus the stress, which is equal to 35 megapascal, multiplied by the length, which is 3000 millimeter, and the modulus of elasticity of 80 times 10 cubed megapascal. And in this equation, you will notice that the following will cancel, meter will cancel, megapascal will also cancel, as well as millimeter will cancel on both ends. At ang matitirang quantity lamang dito is this change in temperature having a unit of degree Celsius. So if this will be simplified, we shall be getting a change in temperature which is equal to 70.6 degrees Celsius. But how do we compute for the change in temperature? Because in the problem, it is not the change in temperature which that is us, but the final temperature, the temperature at which the stress will be 35 megapascal, given that we know the initial temperature. So knowing that the change in temperature is the difference between the final and the initial temperature, and in the problem it is already taken to be equal to 70.6 degrees Celsius. So if we will be substituting the value of the initial temperature of negative 20, therefore we can solve for the final temperature being equal to E sub 2 minus the negative 20 shall be equal to 70.6 degrees Celsius. And then simplifying, we shall be getting the final temperature T sub 2, which is equal to 50.6 degrees Celsius. And so this is how we show the solution, using the systematic approach in dealing with this kind of problem. And I hope that you are able to follow that. First example that I have prepared for you. Our second problem is similarly interesting problem, which I also have taken from the book of Singer. However, I added this part, letter B, in order for us to further strengthen our understanding with the thermal stresses. And here is the problem. Calculate the increase in stress for each segment of the compound bar shown in the figure. if the temperature is increased by 100 degrees Fahrenheit, assuming that the bars are suitably braced against buckling, and letter A, the supports are unyielding, meaning here the supports are rigid. And letter B, the supports spring together a total distance of 0.005 inch. So in our solution, we are given here a compound bars that is composed of aluminum and steel, given the length of 10 inches for the aluminum and 15 inches for the steel, as well as the other properties like the modulus of elasticity, the area, and the coefficient of linear expansion for both the aluminum and the steel. It is said that in the problem it will be the temperature will increase by 100 degrees Fahrenheit, meaning there will be a change in temperature which is equivalent to 100 degrees Fahrenheit. And in this case, we shall be required to determine what shall be the increase in the stress in both, the steel and the aluminum. Okay, so in this case, we shall be again using the same approach that I have presented. So sabi yan, let us try to imagine that we remove all the constraints and all loads if possible, and we allow the deformation to occur freely whenever there will be a change in temperature. Sabi dito, the temperature will increase by 100 degrees Fahrenheit. So we will be expecting that both the aluminum and steel shall be elongated due to the change in temperature. So what shall we do is we will be showing the elongation of this aluminum and steel by removing for the moment one of the ends. So we will be removing this right end, and we allow the aluminum and steel to deform, to increase due to the change in temperature. Let us try to do it. Okay, tinanggal ko na yung ating load, iniwan ko na ang shadow para meron tayong reference where it will be returned back. Okay, so ang gagawin natin dito para mas maliwanag ay isa-isa nating ipakikita kung paano siya nagkaroon ng deformation. We will start with showing the deformation of the aluminum due to the change in temperature. And this is what will happen. Okay, nakita niyo na at this moment, humaba yung aluminum, pero hindi ko muna ipinakita yung paghaba ng steel, So doon muna tayo sa pansamantala doon sa paghaba ng aluminum. Okay, so at this moment, tingnan natin na humaba yung aluminum, so that this distance from the original to this point at the end of the aluminum after elongation is called as the deformation on the aluminum due to the change in temperature. At dahil wala pang paghaba itong steel, so asahan natin mula dito hanggang dito sa end nito will also be the same as this deformation, di ba? So I will be calling it as the deformation on the aluminum due to the change in temperature. For the meantime, aluminum pa lang ang humahaba dito, pero ang steel haba din, di ba? So makatuwid, we have to show the elongation of the steel due to the same change in temperature. And so I will show it this way. So may paghaba uli, may paghaba pa rin yung tinatawag nating steel. And we will be using this as the deformation on the steel, due to the change in temperature. So makatuwid, yung end ng steel ay narito na, samantalang yung kanyang original support ay nandito pa. Diba, narito? So kung wala yung support, ganyan yung mangyayari sa aluminum and steel, and there will be no stress because the deformations are allowed freely. But because there is the wall, we have to bring back the wall. So how are we going to bring back the wall if the end of the steel is already beyond that wall? So we need to apply an internal load to bring it back to original form of restraint. So we have to bring back the wall at this point. So what shall we do is to induce now, create now a deformation due to this P, so that we can bring back the wall at this position. So we have to consider bringing it back that. So we can bring back the wall, pakita ko ulit, in that position. Di ba? So kung naibalik na natin siya, ano ngayon ang nangyari mula doon sa dulo kanina ng steel hanggang sa naibalik to? Itong length na ito ngayon will become the sum of what? the sum of the deformations in the aluminum and in the steel due to this induced or internal force that's developed caused by the change in temperature. So that if we were to consider finding the geometric relationship between those deformations, we can say that this sum shall be equal to this sum. So that we're going to sum up the deformation. The total deformation due to the load P shall be equal to the deformation caused by the change in temperature in both materials, the aluminum and the steel. Diba? So that if we're going to substitute the values, the formula, our deformation is given by the formula PL over AE. So that I have here PL over AE of the aluminum plus PL over AE of the steel shall be equal to alpha L delta T of the aluminum plus alpha L delta T of the steel. Knowing that we are given the following, we're going to sum up, apply the condition of equilibrium. We will expect, or we will, learn that, the internal load acting on the aluminum is also the same as the internal load acting on the steel, and that is equal to the load P that we have shown to be acting here. So that if this will be substituted here, as well as substituting all the other values in the problem, therefore our equation becomes equal to P multiplied by 10 divided by 2 times 10 to the 6 psi. For the steel, you have P multiplied by 15 divided by 1.5 times 29 times 10 to the 6 psi, and this shall be equal to the following: alpha of alpha L delta T of the aluminum, we have 12.8 times 10 to the negative 6 multiplied by 10 inches multiplied by 100 degrees Fahrenheit plus 6.5 times 10 to the negative 6 for the steel times 15 inches multiplied by 100 degrees Fahrenheit. And in this equation, we only have one unknown P, the internal load that is developed between on the aluminum and steel due to the change in temperature. And if we're going to use our calculator, entering this equation in our calculator, you can solve for the P, which is equal to 20,691.84 pounds. And so if we're going to solve for the stress, that stress is equal to the ratio of P over A. So that for the aluminum, the stress will be equal to P of the aluminum over the area of the aluminum, where P of the aluminum is equal to that of P that is already computed. Then we do have here an equation equal to 26,691.84 divided by 2, so that becomes equal to 13,345.92 psi. While for the steel, we shall have here a stress equal to P of the steel over area of the steel, and that we have here equal to 26,691.84 divided by 1.5, that our stress in the steel becomes equal to 17.794.56 psi. And so this becomes now the stresses on the aluminum and the steel. Take note that in the first problem, the supports there are unyielding, meaning the supports remains at the same position when the temperature changes. Now, what about the second question? According to the second question, we will be finding for the stresses developed when the temperature increases by 120, considering that the supports spring together at total distance of 0.005. Siguro magandang maunawa natin ano ba yung ibig sabihin ng spring together. Ang ibig sabihin nun ganito, no? Kapag gumalaw siya, kapag nag-increase yung temperature, may tutulak ng konti yung wall, ano? By an amount of 0.005. 0.005. This is 0.005. So may tutulak siya. This is what we mean by spring together. So that if the temperature nawala, balik lang ulit siya sa dati. Diba? Kapag nag-increase yung temperature niya, there will be, the wall will yield a distance of 0.005 as given in the problem, of an inch. And so we are required here to find what will be now the stress developed on the material. Okay? So, ganun din ang mangyayari na we will be doing the same as in the first part of our solution. What shall we do is to consider removing removing the constraint or the support so that we will be allowing the deformation to occur freely. And so if we will be removing that support and then we allow the deformation to occur freely, we do show it one by one. Again, we have here the deformation on the aluminum, which shall be also equal to this amount. Considering that on the aluminum has increased for the moment, but after the increase in the steel, the steel would also increase and there will be a deformation of the steel equal to this one, alpha delta S sub T. So we will have to bring it back. We have to bring it back. But not anymore on the original form, but on the position after it has spring together. After the wall has moved a total distance of 0.005. Pag ibinalik yan, dito na lamang siya ibabalik. Yun, doon na lang siya ibabalik. Okay? Hanggang dyan na lamang siya ibabalik. Because at that point, nandiyan na ngayon yung tinatawag nating wall. Nagkaroon na siya ng springing of the wall. So, this amount is 0.005 while this amount will be equal to the sum of delta A, or deformation of the aluminum, and the deformation of the steel. And if we're going to consider finding for the relationship between the two, anong relation meron tayo? We'll notice that the sum of these three will be equal to this deformation. So that you'll have change in deformation on aluminum and steel due to P, plus the springing of the wall of 0.005 shall be equal to the deformation due to the change in temperature of the aluminum and that of the steel. And again, if we're going to substitute the formula that I have for the aluminum, plus PL over A of the steel plus 0.005 shall be equal to alpha L delta T of aluminum plus alpha L delta T of the steel. So that if we are going to again apply the condition of the equilibrium, you will expect here that the P of the aluminum shall be equal to the P of the steel, which is also equal to that applied load P. And so if this will be substituted, we shall have here equation for PL over A of the aluminum plus the PL over A of the steel plus 0.005, which is the spring together, shall be equal to alpha L delta T of the aluminum, and here you have alpha L delta T of the steel. And again, you will notice that you have here an equation with only one unknown P, where P can be solved by entering it in your calculator, so that P now can be solved to be 20,773.47. With this P computed, so we can now solve for the stress in the aluminum and in the steel. Therefore, for the aluminum, using the formula that P stress is equal to P over A, so we shall have here stress in the aluminum equal to 20,773.47 divided by 2 inches, and that is equal to 10,386.73 psi. While for the steel, using the same formula, that stress is equal to PS over AS, so we have the stress in the steel equal to 20,773.47 pounds divided by 1.5 square inch, and so our stress becomes equal to 13,848.98 psi. So that is how we solve it. At this time, we have shown that the wall springs together. The key is that we shall be able to establish the geometric relationship between the deformations on the material caused by the change in temperature, as well as the deformation that is supposed to be induced by the internal load that is created by the increase in temperature, and after which we can easily now solve for the problem. I hope, guys, that you are able to follow the solution that I have presented, and with this problem that I have given you, you have now the guts to solve your own problems that will deal with thermal stresses. Now, for the third problem, I also have here another problem which I took from the same book, the book of Singer. And this is somewhat interesting because finding for the relationship between the deformation is somehow uh, needs analysis, further analysis of the system. And the problem goes like this one. A rigid horizontal bar of negligible mass is connected to two rods as shown in the figure. If the system is initially stress-free, calculate the temperature change that will cause a tensile stress of 90 megapascal in the brass rod. Assume that both rods are subjected to change in temperature. Dito medyo mayroon akong gustong ipaunawa, no? Kasi kinakailangan makita natin dito in what direction is the change in temperature occur, or will the change in temperature occur. Because it is expected that the brass rod is 1, will be subjected to a tensile stress of 90 megapascal after the change in temperature. Okay, the question is, in what sense do we have for the change in temperature? So, ang ibig sabihin kasi nito, at the end, itong brass ay hinahatak. Di ba? Hinahatak. Ibig sabihin, bakit siya hatakin? Kasi maaaring siya ay umikli na. Di ba? Kasi kung sakaling walang paggalaw, halimbawa itong structure, kung itong AB will remain in the same position, kinakailangang hatakin itong brass nito kung iikli siya. Di ba? But because the problem states that the brass will be subjected to a tensile stress, ibig sabihin, nung magkaroon ng change in temperature, umikli yung brass. Di ba? So, ibig sabihin, for the system to be solved, we shall be expecting that the change in temperature is that there will be a drop in the temperature. And that is what we will be looking for. So, now let us try to have it redrawn on a larger scale so that we can easily show the deformation as well as examine the relationship between the deformations that will be caused by the change in temperature and the supposed to be internal loads that will be developed on the material. And here is the larger view of the material or the system. I have made it larger so that I can easily imagine the deformation as well as the relationship between this deformation. So again, we will be applying here the basic steps. Sabi nga yung una, we need to remove all constraints and the applied loads. So wala namang siyang loads. Ang constraint natin lamang dyan ay yung kanyang support dito, yung kanyang pin na narito, di ba? Pakita ko yung pin ito, di ba? Ito yung pin. So kung tatanggalin natin yung pin, tinanggal natin yung pin, di ba? And then we allow the deformation to occur freely due to the change in temperature. Sabihin natin na binawasan natin, nagkaroon na ng change in temperature, and then we are expecting that the change in temperature is reduction, a drop in the change in temperature. So what will happen to the brass and to the copper rod? These two will be shortened. There will now be what we call a deformation on the materials due to the change in temperature. So let us show this deformation. Humikli na sila, no? So pag ikli nila, kinakailangan maunawaan natin alin ba yung may mas malaki ang iikli at mas maliit ang iikli. By observing, or if you may want, you can compute na right away because all the changes, the change in temperature is given. Wala pa palang given, wala pang given. So but we can naman expect which of the two will have a larger or longer deformation from the relation that change in length is directly proportional to the original length and the coefficient of linear expansion. Let us try to observe. For the copper, I have here 3 and 16, diba? If this 3 and 16 will be multiplied, I will be producing about 48. Whereas for the brass, I have for the length of 2 and coefficient of linear expansion of 18. If I will be multiplying 2 and 18, I will only have 36. More or less mga 36, diba? Ibig sabihin, we will be expecting that for every change in temperature, copper will have larger deformation than that of the brass. And so I have here presented a larger deformation here on the copper than that of the brass. Para medyo meron tayo tinatawag na uh, scaling of the deformation. Okay? So, this deformation, pakita natin yung deformation, ba? Ito yung tinatawag nating deformation of what? Deformation of the copper due to the change in temperature. Diba? Samantalang dito naman sa kabila, we'll be showing it that this deformation will be what? The deformation on the brass due to the change in temperature. And I'll use delta L sub B. Diba? So, kung nagkaroon ng deformation, imagine niyo, no? Paano natin ngayon ibabalik itong rigid bar AB? Okay? Paano natin ibabalik yung rigid bar AB kung natanggal na siya ngayon sa copper at the brass? Kung i-connect natin siya sa copper, hindi po pwede kasi nagkaroon lalo ng mas malaking gap between the brass and the end of that bar. Kung sa brass naman natin i-connecta, hindi din po pwede kasi may gap naman doon sa copper, ba? Kaya ano magiging solusyon? Ang magiging solusyon niyan, we try to find for a position of this bar, and then we try to stretch. We stretch both the brass and the copper, so that they could be reattached to the system. So if I will be trying to imagine that this will be the position, kasi nga mas malaki kasi ang inihaba dito, so mas possible na bumaba siya, magkaroon siya ng inclination this direction, di ba? So kung yun ang magiging asahan nating position ng bar AB, therefore we have to pull copper and the pull brass so that this can be reattached to this bar. So we need to apply therefore a force on the copper and a force on the brass, so that if there will be now an axial load on the brass and the copper, this can be restored back to this original. Pwede ko ngayon siyang ibalik ngayon dito, by pulling it that way, di ba? Kapag naibalik na siya ngayon, nagkaroon tayo ngayon ng tinatawag na deformation. But because brass is now stretched by P sub B and copper is stretched by P sub B, so we expect therefore that the copper and the brass will now be subjected to tensile stress. And that is what we will be looking, So how are we going to now solve for the problem? Let us try to start with establishing the relationship between the PC and the PB, diba? The relationship between the stress on the copper and the brass, by getting the relationship also between the PC and the PB. And that is by considering the free body diagram of the horizontal bar. So, pansamantala, tanggalin ko muna yung loads, yung mga other loads, and I'll show that this bar is subjected now to the P of C. Diba? Yun yung pull that, axial load that is acting on the copper. And on this end, I have here the P of B, the pull that is acting on the brass. And if we are to consider summing up moment about A equal to 0, we shall be getting the relationship between PC and PB. So that, summing up moment about A equal to 0, considering that, counterclockwise as positive, our equation becomes equal to P sub B multiplied by 5 minus P sub C multiplied by 3 shall be equal to 0. So that from here, we can say that P sub B is 5P sub B is equal to 3P sub C. But since we will be getting for the relationship between the stress, we know that the stress is equal to P over A, and P can be expressed in terms of the stress, can be expressed in terms of stress, so that, stress sub B multiplied by the cross-sectional area representing this P sub B multiplied by 5 shall be equal to the stress sub C, multiplied by A, multiplied by 3. So if this will be simplified, we can say that, when stress sub B, which is given in the problem to be 90 megapascal, we can substitute the value here, that 90 multiplied by 1200 representing the area of the brass, multiplied by 5 shall be equal to the stress on the copper multiplied by 1500 representing the area of the copper multiplied by 3. And so from here, we can solve for the stress on the copper to be 120 megapascal, meaning when the brass is subjected now to a stress of 90 megapascal due to the change in temperature, the copper is subjected to a stress of 120 degrees megapascal due to the same change in temperature. Now, after that, what shall we do? Now, we try to establish the relationship between the geometric relationship between the elongation caused by, deformation caused by the change in temperature and the deformation caused by these axial loads that causes stress on the material. So, balik ko lamang yung ating sistema kanina at ipakita ko ulit yung loads acting on the copper and on the brass so that when they are pulled, they can be brought to the final condition of restraint. This is what we call final because this is not the original. The original is horizontal. It has inclined at a certain angle. Therefore, this is the final expected form of constraint. Diba? So, sabi nito, we shall be forming the geometric relationship between those deformations caused by the change in temperature as well as the deformation caused by the load acting internally on the materials. Now, let us try to find out what is this deformation mula dito hanggang dito. So, this deformation, pakita natin yan, shall be the deformation of what? The deformation of the copper due to the P sub C. Whereas, from this point, mula dito hanggang dito, kasi kanina may cleaner siya dito, di ba? Hanggang dyan, shall be called what? The deformation on the brass due to P of B. Di ba? So, ang kailangan natin makuha relation among these four. Anong meron relation among those four? So, let us try to find out. Do you see this triangle? Okay. Do you see this triangle? Actually, with this triangle, we can establish the relationship because from the triangle, we can find this side. Ba? Yung kulay yellow. And this yellow one shall be equal to the difference between this change in the length of the copper minus deformation on the copper due to P sub C. Whereas this one, ito, part nito mula dito, yung yellow nito, will be the difference between the deformation on the brass due to P of B minus the change in length in the brass due to the change in temperature. That is what. Diba? And because these are part of the triangle, the two can now be the relationship between the two can be established by using ratio proportion because these are part of the triangle. So that by ratio proportion, so we say that this side is to 3 as this side is to 5. Yun. Diba? So simplifying this one, so the change in length in the copper minus the deformation due to P in the copper shall be equal to 0.6 because I have 3 divided by 5 is 0.6 times the quantity deformation on the brass due to the axial load on the brass minus the deformation on the brass due to the change in temperature. And if all the formula shall be substituted in this equation, we shall have here the following. Alpha L delta T minus PL over AE of the copper shall be equal to 0.6. I will be distributing 0.6 to this side and to the term inside the term so that I will have here 0.6 of PL over AE minus 0.6 of alpha L delta T. Now, from this equation, try to substitute all the given unknowns. So, we shall have here alpha, which is equal to 16.8 times 10 to the 6. Okay. Micrometer. This is micrometer. Here is micrometer. Diba? Micrometer per meter degree Celsius multiplied by 3 meters divided by delta T, which is unknown. Whereas this one is stress on the copper multiplied by 3 divided by 120 times 10 cube megapascal shall be equal to 0.6 of stress in the bronze multiplied by 2 divided by 100 times 10 cube megapascal minus 0.6 of alpha L delta T. Diba? So if the stress on the copper and on the brass will be substituted in the formula, we shall have here the equations. So if substitute ko na lamang dito, shall be equal to 0.6 multiplied by 90 times 2 divided by 100 times 10 cubed minus the same point and so on and so forth. And that, okay, simplifying for solving for delta t, because we have here an equation that involves only one unknown, delta t, and delta t therefore can be solved at 56.01 degrees Celsius. These are the solution to the problems that I have given you. And I hope that you are able to follow the solution that I have presented to you, and having this scene, you will be able to solve your own any problem that will deal with thermal stresses. Once again, thank you very much for watching.